Right, recorded.
Okay, I will just start then. Okay, so welcome back to the last seminar of the year. Um, yeah, I hope if you observe solstice-related cultural events that you're having a good one. It's a really dark time of the year, so it's important to remember to be nice to people. Don't be a jerk. Okay, so what I wanted to talk about today is much more relaxed than what we normally talk about, even though I maybe go into a lot of detail here and there. I'll start out with some recap. I don't really have to go into this much detail, but I just wanted to recall some of the stuff we talked about in the summer so that it wasn't just for nothing. Um, and then I'm going to talk about the fundamental group, which, if you remember, this is related to loops in a topological space. And you can use these loops up to continuous deformation to detect like holes in your space and things like that. So like I said in the abstract, in principle, the fundamental group can be any abelian, or sorry, any topological, sorry, already saying things wrong. Fundamental group can in principle be any group. So you can always construct some space that has that fundamental group. But if your space itself has a continuous group structure, then it turns out that the fundamental group is always abelian. And this is a really interesting phenomenon, and it uses the group structure in a central way. So you can sit down and just write out the homotopy that witnesses the commutativity, but you can also sort of push the abstraction higher and higher and higher to find other contexts where it's a little bit more clear why you get this commutativity. It's not just some magical coincidence that only happens for fundamental groups of a topological group. There's something deeper going on. So I'm going to expose that deeper thing going on. The motivation for this talk, for the inspiration, was a map.stack exchange question that I read like 8 years ago, and I couldn't find a link to it. It just suggested that there was another way of doing this that's a little more systematic than just writing something down. So I worked it out, and now I have a big talk that I can give about it. But first, we're going to do recap, and I'll just go quickly through it because this is just the basics of topological spaces and some notions of homotopy theory, just to put us all on the same page. Okay, so first things first, in homotopy, especially with fundamental groups, you're often concerned about spaces that already have a point chosen for us. So in particular, if you talk about a group, well, right, every group has an identity element. There's sort of natural choice for a base point. You might just want to work in general with spaces that have a choice of a base point already. These are called pointed spaces, and we're going to call the category of pointed spaces top star, just to mimic category top of topological spaces. All it is a topological space and a base and a choice of point in it. You can talk about the morphisms in this category. The pointed continuous function or pointed map is a lot faster to write. Given two pointed spaces, you just want a continuous function that takes one of the base points to the other. So the only additional structure that you have on this top star is that you have this choice base point, and so the morphisms in this finer category just have to respect that additional structure of mapping a base point to a base point. So everything's kind of like tethered at the base point. So there.
If the like x dot or x naught and y naught are the identity, this just reduces down to just regular like category of topologies, no? Because identity morphisms preserve the identity, right?
I think you're conflating two things. So this is just topological spaces. So we haven't actually started talking about topological groups yet.
Oh, okay.
Yeah.
Okay.
And so in general, like one difference is that there's an empty topological space, but that's not a pointed space.
Yeah, okay.
So these categories actually are very different structurally like that.
Okay.
So it's a good question. So the topological spaces, this is a good point. The initial object is the empty space. There's always an embedding of the empty space into any other space. The terminal object is a singleton point. Every space maps canonically to a singleton. Whereas in top star, there is no empty thing. The singleton space is also initial because you just have that one base point, and your only thing you can do is map it to the base point of the target. So you're already determined. And the terminal object, again, is the same. It's also the singleton. So in fact, a singleton space is terminal and initial. So this has a zero object in it, whereas top does not have a zero object. So that's kind of from an algebraic level, at the level of categories, it's more convenient to have this pointed category because like it has a zero in it, not just a distinct terminal and initial objects. So using this idea of like having a zero thing that we can always have flying around, our wedge, so our topological spaces, the natural thing to do is form a disjoint union of two of them. But if you have a base point in each of them, there's no canonical choice of what should be the base point of the disjoint union. And so in a pointed context, the solution to that is to just glue those two base points together. And now you have this canonical equivalence class of base points. So that's the definition of our wedge product. You start by taking the disjoint union of x and y, and then you glue together their two base points. So it's a picture, here's the two sphere, and here's a one sphere. And then their wedge product, you really just wedge them together, glue them together at this chosen base point. And so this is the analog of a disjoint union, or more generally, you call this a coproduct. This is the coproduct in the category of pointed spaces, whereas disjoint union is the coproduct in the category of spaces.
If you can write your indices a bit bigger, that would be awesome.
Oh yeah, indices. Okay. Yeah. These a little very small. Yeah. So the Cartesian product, well, there still is a canonical choice of base point, and that is just taking the pair, right? So this is a pointed space with the pair of base point. So the Cartesian product still is the product construction in the category of pointed spaces, but there's also a different kind of product that we want to consider instead, which has a lot of convenient topological properties. So notice that inside the Cartesian product, there's actually a natural embedding of the wedge product. So you can define a function on the wedge product. Like I said, it's the coproduct. You just have to define it on each piece. And since it's compatible with the base point by construction, so you just have to give a morphism on each piece. Being a morphism means that it respects the base point, maps the base point to the image. And so you're going to be able to define a function on the space that's glued together. It's going to be well defined. So you just take your x part to, that's incorrect. Oh boy, I wasn't paying attention. Yeah, so whatever you have in your x coordinate, you take to x with the y base point, and whatever you have in the y coordinate, you take to the x base point, comma, y. And so as a picture, this is a picture of what this natural embedding looks like in the torus. So the torus is the Cartesian product of two copies of S1, and the wedge product of two copies of S1 is this like figure eight space. And so here I've drawn the torus, and I've drawn like the meridian circle and the latitude or the longitude circle, whatever that was called. You see this wedge product living inside of the torus. So here's the base point across one copy of the circle, and then kind of looking in the opposite kind of orthogonal perspective, you get the other copy of the circle across the base point. And so our preferred product, or maybe our alternative product, is called the smash product. And what you do is you take this Cartesian product with its canonically embedded wedge, and you crunch that down to a point. This is what I'm doing. And the base point that you choose is going to be, the equivalence class of the wedge. So this drawing illustrates how that happens. So I decided to do the quotient in two stages. I take the quotient of this copy first to get a little pinched point there. And then we still have the other copy going around the middle. Now you can imagine that when you take that copy and shrink it down, that whole circle gets crunched down to that point. And what you're left behind with looks more or less like a two-dimensional sphere. And the reality is that if you choose base points, of course, this is a statement about pointed spaces. Wedge product only really makes sense for pointed spaces, or smash product. If you smash two spheres together, you actually just get the sphere whose dimension is the sum of the two dimensions. Okay, so that's just a recap about wedge and smash. So now let's think about homotopies.
Question.
Yeah.
For that ends up being homeomorphic to S2, right? With a base point.
Yeah.
And is there anything weird happening at the base point because it's pinched?
Like in terms of smooth structures,
Yeah,
like it's
yeah.
not clear how you would take the smooth structure on the torus and induce one on the sphere in like an arbitrary context. Yeah, there is something weird at the base point. It is pinched.
Because topologically, there's nothing weird going on, but geometrically, there could be.
Yeah, I don't think you can make exotics, but not sure. But it's like, yeah, once you've taken that quotient, like it's not like a good quotient. So you just pop out of the smooth category. You have to make a choice now about how to put a smooth structure on the quotient. Yeah. Okay. Yeah. So we're not talking about smooth stuff. Daniel keeps trying to convince me that I like differential geometry, and I keep having to say, no, I don't. I'm just talking about topological things today. So let's go with the homotopy now. What is a homotopy? In principle, by definition, it's just a continuous function from x cross the interval to some other space y. And so you want to think about a homotopy as being like a movie of function. You have this movie variable, your time parameter, that like as you go from t from 0 to 1, it's like you're cranking a projector that starts at one function of x and ends up at another function of x. So given two functions f and g, we say that they're homotopic. If there is a homotopy where the restriction to 0 gives the first one back and the restriction to 1 gives the other one. And you can draw this, it's a diagram like this.
What do you mean by like the restriction to 0? Oh,
Yeah,
like
I
the
mean
first,
exactly like this.
Yeah,
So you
yeah,
embed
okay.
x
Yeah.
as x cross 0.
yeah, then you
And
can, yeah.
and follow through with that h composer. I guess these don't have to be dotted line. Literally just say equals as functions. Okay.
Mhm.
Draw that.
And I don't want to be too pedantic, but is it true that the map from X to X cross I is an injective
Yeah, you
map?
want me to put little hooks on?
Yeah, the hooks thingies that you always do.
Look, those are embeddings. That's fine. H doesn't have to be injective or surjective or anything. It's just continuous. Same with F and G. Okay, so that's a homotopy. If we want to think about homotopies in the context of pointed spaces, well, it's natural just to require that the base point be fixed for all time. It turns out a very convenient way of writing that down is to say that H is a map from X smash I plus to Y. So here I plus, this is a construction you do for any space. Just take the disjoint union with an additional point, you call it plus. So it's not a one-point compactification, it's literally a disjoint union. You just have another point sitting there out there in space. Here, X and Y are pointed spaces. So why is this the right thing to do? Well, let's look at, well, it's one correct thing to do. So here's diagrammatically what's happening. This is a picture of X cross I plus. This is X cross I, and this is the X cross the plus part. So where do we find the wedge? X wedge I plus. Well, here's X cross the base point of I plus. Here's the base point of X cross I. So this doesn't quite have base point of X cross I plus, but this is the base point of X cross I plus. So the union of these two green parts is the wedge product of X cross I plus. Sorry, the smash product, X and Y plus. And when you take the quotient by this, well, you're just crunching that down to a point, crunching that down to a point, and then moving those 2 points together. So in essence, all we've really done is taken the cylinder on X and then crunched down the ray that's, where you have X naught fixed. So having this entire line getting crunched down to 1 point means that a function out of X cross smash plus, or X smash I plus, the same as a function out of X cross I, so that you fix the base point for all time. It's just a really convenient thing. that I wanted to show off because I think it's a really extremely complicated way of saying something very simple. So you can also talk about the same pointed homotopic for two functions. So if you look at this quotient, if you look at each of the copies of x mapping into this, well, for each time you actually still get an embedding of x into this pinched cylinder. So x cross 0 is still an embedding, x cross 1 is still an embedding, and you can just follow those embeddings through with h, and then you can ask whether that's the same as f or g. Okay. Complicated way of saying the homotopy that fixes the base point for all time.
I mean, yeah, in principle, they're the exact same. I mean, they are the same things. Just one of them, you're fixing the base point, right?
Yeah,
Yeah.
yeah, it's just meaninglessly verbose way of doing it.
Yeah.
Just wanted to not waste all that stuff we've already done. Okay, exercise. Show that these are equivalence relation. So given two functions f and g on the same, So if you consider all of the functions that are homotopic, that forms an equivalence class, this relation. It's easy to see, I guess, all of these properties are easy to show. Reflexivity, you can just take like a constant h, so it doesn't vary with time. To show symmetry, you can just run your homotopy backwards. And then if you want transitivity, you can just compose homotopies. We'll see a little more about composing homotopies when we start composing paths. But so this will be an exercise for you just to verify this. So we can go and we can form sets. So given spaces, we might have a base point. So this is the notation for the homotopy classes of maps from X to Y. I'll just write map as my mapping space. I guess this definition doesn't require this to have topology. So this will just be the set of all maps, continuous functions from X to Y, and we say two of them are equivalent if they're homotopic. If we think a little harder and we did put the correct topology on this, a homotopy would just be a path in this space. In fact, like this is one of the main motivations for compact open topology is precisely so that a homotopy becomes just a path in the space. But we don't actually need that topology since we're already quotienting by the correct equivalence relation. This is going to be the pointed maps. Take a pointed map, find a pointed homotopy. And more generally, you can talk about homotopies that fix the base point for all time, but you can also just take an arbitrary subset A, which should be of X. Take an arbitrary subset of X, and you can talk about homotopy relative A, and that's just something that fixes that subset for all time. Like an analogous. Okay. So that's the basic stuff that I wanted to just get everyone on the same page. And now we can talk about fundamental proofs. So let's consider applications of all these ideas. So let's let x0 and then we want to consider, like I said, we want to consider basic loops. And so you can right off the bat consider pointed homotopy classes of maps from the circle to X. So this is a perfectly good space, or set rather. And if this is not 0, then you can tell that X has non-trivial topology. But if X is contractible, then of course, like everything is going to be homotopic to the base point. And so if X is contractible, this is going to be a singleton. If it's not a singleton, then X is not contractible. Computing this in general, just from the definition, is not exactly easy. The thing that makes it easy is that we can actually, not easy, something that helps us is that we can actually put a group structure on this set. So how does that work? We can also think of this as being mapping from the physical as well, not quite. You can, all right, the notation's failing me now. Let's take the set of all paths gamma with my events start and end at the same point. So gamma 0 equals gamma 1 modulo by homotopy relative to the endpoints 0, 1. So mapping a circle into X and keeping the base point fixed for all time is the same thing as mapping the interval into X and making sure that both of the ends of the interval go to the base point and that they never move from that base point. So these are the same thing. And so let's see, what do they want to do here? Yeah. I think I've already messed up that one. It's okay.
Can you erase the things around gamma, the smudged parts?
Yeah, I can erase it and write it better.
And the video is not clear.
Okay, so just in terms of having nice spaces that I want to work with, I'm going to take homotopies later. Yeah, I'll start following my notes because I had the right idea. Let's call omega x the loop space. And just by definition, I'm going to take this to each point it maps. And then I'm going to have a path space. Oops. So this is going to be maps gamma. So that's 0. And then, yeah, so these are just two expressions of the same thing. What I'm saying is that that's the loop space is homeomorphic to this gamma space. Just using them to have two expressions of the same thing. So it allows me to like translate back and forth between these two notions without getting too confusing with the notation. So I wasn't right when I said we didn't need the topologies on these things. I just forgot what I was thinking about earlier. Okay. Now that we have this gamma, so just taking normal maps from S1 into X, what can you do with that? Well, if you parameterize those loops as paths, now you can do things like do one loop and then do the other one. So we can do this, given pair of loops or a gamma space, find catenation product gamma 0 star gamma 1. This is supposed to be a function on the interval. It takes a t and spits out something in x. This is going to be gamma 0 of 2t. And t is in the first half of the interval. So you're essentially just doing both paths one after the other, but twice as fast. 2t minus 1. T to the second half of the interval. So this is a product, given the parametrization of these paths, this allows us to construct this product. We can concatenate them together. Then caveat, this is not unital, not associative, no inverse.
I mean, obviously it's not unital, but like humor me or whatever, if you have like this zero path where it keeps you at the base point, how is that not like being identity?
Because when you concatenate with that, you're going to be sitting still for half the period, and then doing the other path twice on that. So that's not the same thing. It's The first path.
First path and then the second.
Yeah. So it was like I was talking with Vaughn about this on Discord. He was reading a book that had loops that have variable length. So in that case, you can have an identity where you have like a constant path that means zero.
Yeah, yeah.
And then, but that's just not how we're defining it.
Okay.
Yeah. So in his case, it was unital and it was associative, but there still was
No reverse.
Yeah. Because if you do one loop and then go backwards, that's not even close to even enough.
Yeah.
But it is okay. But so that explains why these things aren't true, but they are true. Up to home. Okay. So let's see why that is. In order to show that these things are true up to homotopy, it suffices to just write down a homotopy for any possible choice of paths that you want to either test a unit on or find an inverse for or verify associativity. So let's begin with unital. You define E in our loop, or yeah, I wanted to say, in my notes I start confusing them already. It's okay. Everyone always just write omega and then just acts like you're circled with parallel tracks. It's okay. I'll just do this. It's confusing, but it's okay. And then we'll yeah. So this is the constant math for every time, just sit still at the identity. So then we're going to define a homotopy called U sub R, and it's going to be a homotopy that depends on gamma. And it's going to have a real parameter S. This is going to be in an interval. And so this is going to be the homotopy between our two paths. So given every homotopy parameter, we're supposed to have a path. And so we're going to plug in a time coordinate for that path. And I'm going to say the value should be 2 minus S times T. If T is in 0 to 1 plus S over 2, and it's going to be X naught, T is in the rest of the interval. Okay, an annoying thing to look at, but let's see what happens at the extreme end. So when S is equal to 0, what does that mean? This is equal to 2T. So U are gamma 0 T equals gamma 2T. And then this is going to be 1 over 2, okay? And otherwise it's not for the rest of the time. So this is just equal to the composition, concatenation of gamma and E of T. And so at the other end, S equals 1. This is now 1 times T, and this is the number 1. And this is X0, but only at the very last moment when T equals 1. So you are gamma 1 of T is equal to gamma. So indeed, U of gamma U are gamma, the homotopy notation I forgot to introduce is a homotopy between this composition and the not composing of the unit. So in other words, we actually get a function UR takes a path, takes a homotopy parameter, and spits out another path. Yeah. Yeah. So this is something that's actually defined on the entire space. You can have like, the function from gamma x to itself, which is multiplying on the right by the identity, or the E, the unit, or you can just have it, map to itself by the identity, and this UR is a homotopy between those two things. So UR gamma specifically goes between these two. The UR is actually a function, the homotopy on the space of paths that goes from the multiplication on the right by the unit to identity. So that's a little more structure, actually, than just writing down a homotopy or whatever for each gamma. You actually have this universally defined natural thing on the entire space. So similarly, there is a UL, which goes from multiplication on the left by the unit to just doing nothing. So these are the unit structures. Okay. Yeah. These were like the easiest ones to write out. Everything else is not so hard, but it's very a lot of writing things down. Are there questions about that so far? So that's pretty stuff's kind of straightforward.
Wait, if S is -1 for, oh no, S is 1.
Yeah,
Sorry.
S is only between 0 and
Sorry, yeah, you have like it's a semicolon. I thought that was comma -1 in
Oh,
the X1 case, but yeah, that makes sense.
yeah.
Because I was thinking -1, and then you don't get gamma t, you get something else.
Yeah, it's not even in the
Yeah, it's not even,
definition,
yeah.
so
Yeah.
don't worry about that. Okay, so let's move to inverses then. So given gamma in our path, find gamma bar t. This is going to be gamma of 1 minus t. So you just do gamma backwards. Now we're going to define I gamma homotopy parameter S going to be gamma of 2st when t is in. Oh yeah, this is actually nice. This is the only case where the endpoints of the interval don't move. 2s 1 minus t. Continue the rest of the line. Okay, so s is equal to 0. This is obviously just do nothing forever, right? You just plug in 0 to gamma, plug in 0 to gamma, you just get the base point forever. This is x0 for all t. The s0, you get e. This is equal to 1. What do you get? You get gamma of 2t. Then you go from gamma twice as fast. And then you get gamma of 1 minus t. And so, yeah, it's not immediately obvious, but if you take this and work it out, this is equal to gamma bar of 1 minus t. No? 2t minus 1. 2t minus 1. And so this piecewise thing is by definition gamma concatenated with gamma bar. So there's our inverse up to homotopy. So given going gamma and then back, right? Like it's still tethered at the start and end. But like when you get to the base point along gamma, you're only halfway through your actual path. So the idea of this homotopy is you just do less and less of gamma as s goes from like 1 down to 0. And so like when s finally gets down to 0, you just don't do any of gamma, just sit still. So this was confusing to me the very first time I learned it, because I thought, well, if you go from gamma to here and then go back, aren't you like stuck here when you're halfway through? And you're not, because you're at t equals 2. So doing homotopy relative to 0 and 1, right? When t equals 1 over 2, it doesn't care about that. You can just don't go all the way through your first path. It's fine. And then there's associativity. I think I'll try not to say too much about that. It's just kind of annoying. I'll just say what the answer. or at least the answer that I came up with off the top of my head while I was sitting down and working this out late one night for fun. Okay, so for gamma 1, gamma 2, gamma 3, line A, associator, these things. And then it's going to be at time t. You will do gamma 1 at this rate, or these times. Gamma 2. So all we're really doing is just changing the rate at which we're going through our paths, or loops rather, and changing the duration that it's taking us to go through each loop. And it's not extremely hard to figure out all of these endpoints. You just have to think about convex linear combinations and stuff. It's very tedious, but you can do it. And then this associator between the two paths, three paths, sorry. This goes from gamma 1, gamma 3, 3 to gamma 1. All right, so going to summarize what we just did. It's kind of interesting to see phrase to this way. Summary. So we have operation, star. Yeah, I'll just use loops now because it's hard to just write the gammas all the time and you're used to using them. We have an operation called star. And the following commute up to homotopy. So first, you have omega maps to itself along, yeah. And we had our homotopy going this way, R. And then we also have a L. So these are our unit homotopies. Yeah, and we have this unit map giving us these unit homotopies. And we have an inversion homotopy. So if we start with gamma x, we take it, right, a map into a product which is given by its coordinates. So our coordinates are going to be take the identity, gamma goes to gamma, and then take a gamma to gamma bar. So yeah, gamma goes to gamma cross gamma bar. And then we just compose those together to get gamma cross gamma bar, or gamma times gamma bar. And here we have the identity, sorry, not the identity, this is just a constant map E. So this is a constant map. And our homotopy that we found is I. So it says that this map is null homotopy. Where the identity concatenated with the identity bar is null homotopic. Our I that we came up with was a null homotopy. And then finally, there's just the associativity. Three topologists in favor of I wouldn't be belaboring this if this wasn't like a preview of something that's going to come up here. So associativity, right? You can go around the square in two different ways, depending on what order you do your concatenation in. So if you do it in the left two biggies, and then do it in the rest, versus doing it in the right two spots. So then we had our associator homotopy going with this. So this is our loop space, not a group, but it's extremely close to being a group. In the sense that it's a group up to homotopy, but we actually have like global homotopies doing it for us. You don't have to pick a path and do it for each path individually. We actually have these things at the set-wise level. So the abstraction of this structure is called an H space. So I'll write it more worthily. So omega x, also gamma x, because they said do the same thing, is an H space. Precisely just means this, something that has all of the group axioms up to homotopy. Or I guess some people call it specifically an associative H space. So given an H space, it's set at components for a group. Set of path components gets the name pi0. So we're going to define pi1 x 0 want to be the group that we get out of loop snacks. So here is really annoying fundamental group definition. Fundamental group. Here we finally have a definition of a fundamental group, which I could have done in like 5 minutes, but I wanted to go through really be elaborate about presenting it as something that isn't like accidentally a group. There's this construction called loops, which has this really, really rich topological structure, and then we take the path components of it, then we get a group that's called a fundamental.
Wait, but I thought omega was the path. Wait, hold on.
Yeah, oh yeah, okay.
So what does it mean pi0 of omega? I mean, isn't that just the path components of paths?
Yeah.
Okay. Oh, okay. All right.
Yeah, so exactly, right? So normally every time you see the fundamental group defined, you have loops and you take homotopy classes of those loops.
Oh, okay.
So
Okay,
this is a
okay.
space of loops.
Loops. Yeah.
And I completely wiped the topology under the rug,
Yeah.
but the paths in this space are precisely the homotopies of
Okay.
the loops.
Okay.
Yeah.
Sorry, just like written like that made it seem like we were just doing paths of paths.
We are-
Which is exactly what it is, but you know, when I read it in my head, it's like, oh, but
So in general, IN, well, you can iterate this procedure. You take the whole path, homotopy, take the path components of the n-fold iterated paths. So you're doing paths of paths of paths of paths of paths. N times. Geometrically, you can represent that by pointed homotopy classes of maps from the n sphere into S. But this interpretation automatically gives it a group structure because you're taking path components of a loop space. It's an H space.
so it's like a group up to homotopy, right? Because
Yeah.
we only said that all this stuff. Yeah, the H.
The H spaces, yeah. But like as soon as you take the pi0, it is a group path.
Yeah, okay.
So pi n is a group. It's not immediately clear why it is from this definition, but the group structure essentially comes down to fixing coordinates for your sphere. And like, you just take one of your directions, the concatenation direction, and you can just kind of juxtapose two maps of the sphere. This formalism wraps all of that up into like the loop space. So this is this step here is actually like really conceptually cool. Has a lot of big ramifications in topology. It has to do with the loops. Oh no, loops suspension and junction. I didn't talk about suspension, so I won't get into that, but
Also,
this is the loop suspension and junction.
oh, okay, I was gonna say, it's not immediately clear why that isomorphism is kind of,
Immediately, but this is true. That's essentially why.
sorry, some of X.
That's the suspension.
Yeah.
Yeah.
Okay.
So this n sphere is the n-fold suspension of the zero sphere. And so you take that n-fold suspension and move it to the other side, right? This is actually just.
Oh,
pointed
okay,
back
that
to
gives
the
you the
zero
loops.
sphere. The omega n of x. So.
Okay.
So there's some sneakiness going on.
Interesting.
Yeah, a more geometric way to see this is when you have paths of paths of paths, you have coordinates like t1 up to tn. So you're looking at a cube, an n-dimensional cube, and all of the endpoints have to go to zero. So you're taking the boundary of that cube and crunching that down to
To a point, yeah,
So that's
and then you get, oh, okay, neat. Okay, I think I see it now.
Yeah. So yeah, this is like the topologist way of seeing.
Okay.
It's true.
Yeah.
Was
Same idea, but it's just like one coordinate at a time.
was your notation for the reduced suspension?
That is. These are pointed space.
What was your notation for suspension again?
I think I use S.
Oh.
Kind of just depends on the day. Okay, but great, we defined a fundamental group. Fine.
No,
No.
it's 410.
Okay, daylight saving. Okay. So,
Oh, yeah, what the heck? It's a whole hour.
here's an example about three. So one example that I think was mentioned already. X is contractible. Meaning that the identity function is homotopic to the base point. Then I1x. In fact, all of the homotopy groups. All them. And this is just because if the identity map is contractible, then any other function mapping into X, you just contract the identity map down to X naught, and so like everything is going to be. Here is a ordinary. Try to go out. Okay. Next example, which is the very, very famous one. I'd like to write out a full complete proof for you, but there's no time. So you take the circle itself, maps from the circle itself, then you get one homotopy class for each integer. And the intuition is that, okay, well, when we take a loop and you wrap it around n times around the circle, that should correspond to the integer n, right? Doing it twice versus doing it 3 times, those should be different things. And somehow you have to convince yourself that every other loop is homotopic to one of those standard loops. And the mechanism by which you do that, show that every loop is homotopic to one of those standard loops. It depends on your approach. In almost all cases, you're just applying the homotopy lifting property. So really, this argument really comes down to the homotopy lifting property. Even when you do the complex analysis proof, like the complex logarithm is the homotopy lifting property for the complex exponential map. They're not even like conceptually related, it's literally the same thing. So the easiest, yeah. So most of the proofs are going to be homotopy lifting property. The easiest way to write down a map is by using complex analysis. Suppose that the circle is sitting inside the complex plane. You're avoiding 0, and so you can divide by the value of your path. So you can take your contour integral along your path gamma, the function 1 over z d, and then you normalize by the usual stuff, 2 pi I. This is called the winding number. So it's easy to write this down, you still have to prove that it works. But this is the easiest way to play. That's fine, it's the integers. Okay. Another example, if you take the fundamental group of S1 wedge S1, remember that was the figure 8 space. This is the free product of 2 copies of the integers. So this is the group that has two generators, one for this copy, one for this copy, and no relation. So this is not abelian. There's no relation between the two generators at all. It's just all words in two letters. All words. A, B, and also their inverses. Okay, so the proof of this is via a very, very useful thing called the cipher-fit cabinet. So this is the result about fundamental groups that tells you how to compute it when you're sort of gluing them together along like a nicely embedded subspace.
So that like if you had like the fundamental group of anything wedge, anything, it would be the free product between the fundamental groups of the two things.
Yes.
Okay.
Yeah, for the fundamental group, that's true. And then higher homotopy groups, it's like infinitely more common.
Okay. Okay.
Really hard to compute. The higher homotopy groups of a wedge. But yeah, so for any wedge product, you get the free product of the fundamental group. The nice word of that. Okay, and then, yeah, it's multiplicative. And the proof is canonical. So to get a map into a product of these two groups, you have to define it on coordinates. So given a gamma that's in the space, you can project it onto X and project it onto Y. So gamma goes to X gamma plus Y gamma. The other way, just as easy. Given two homotopy classes, you just take it to the homotopy classes of the product. And so you have to check well-definedness and everything like this, but this is how it works. Very, very easy. And it's very important later that it is multiplicative. And then, so an example for that would then be, of course, I1 S1 cross S1. Torus, this is Z cross. Okay, so you could keep trying to find things out. And so here's some examples. Yeah, well, so it definitely doesn't have to be abelian. Like I said, it can be very, very bad abelian. But every example that we've written down so far, which is the group, turns out to be abelian. S1 cross S1, right? This is even true of all tori. So the n-dimensional torus, fundamental group is Z to the n. I1 of UN is also Z. Is actually the determinant map that's using isomorphism. Yeah. Should I bother with that example? Maybe. Sure. Yeah, so G is a group presentation. So I'm going to write a group with a presentation like this. So there's a generating set gamma, and there's a relation set R. Construct quotient. So you can take the wedge, a huge wedge product over all gamma and gamma, a circle, and what do we do? Where do we do that? Yeah. Okay. Right. Okay, yeah. So what you can do is you can take the big wedge over all gamma and gamma. So the fundamental group of this thing is going to be the free group on gamma.
Like the wedge is wedge, the same wedge we're always talking about here?
Yeah.
Okay.
So just wedging together a whole bunch of circles.
Yeah.
So, and then for each of my relations, that's also a word in these gammas. So I can take a circle and just trace out the word using that circle over here. And we construct the quotient where we glue on disks, right, like this, I guess. So we each of these circles is included into a disk. And so what we do is we construct the push-out diagram, which tells us for each of these relations, each of these words in gamma, glue on a disk. So I'm going to call this S, G. Use this notation for push-out diagram. And then say that I1 of X, G is isomorphic to G. So this is really sweeping a lot of things under the carpet here. You can construct this space in this way to have the correct fundamental group, at least for like a countably presented group. I'm not sure if uncountable things will break something, I don't remember. You can in principle get any group. So let's think about more specific types of spaces. So a topological group is a topological space with a continuous group structure called dots, goes from G to G. So by saying group structure, I'm meaning that there are inverses, there is a unit, it is associative. And we also want to require that the inversion map is continuous. Okay. So this is a topological group, kind of exactly what you expect it to be. It's just a topological space that's also a group in the most convenient possible way. And
Often reminiscent of like the group, because
this. So if you replace topological with smooth,
yeah,
you would get a Lie group. Yeah, that's very interesting. Interesting observation. Okay, so theorem. This is sort of the main statement of the talk that like an hour in and I just got to it. If G is a topological group, then I1G is abelian. So if you do this perverse construction on some non-abelian group, then you know automatically that the space that you spit out does not admit a group structure or a continuous group structure. This actually obstructs you from being able to put continuous group structures on the space. Okay.
what about the reverse? Is that
Like,
if the fundamental group is Abelian, does that mean our
no.
underlying thing is okay?
So the family of spheres is like the very big counterexample to that. So there's only a finite number of spheres that admit a group structure.
Okay.
For all of their fundamental groups are
Our
Abelian.
Abelian. True.
Usually zero.
Yeah.
So, it's definitely a subtle question. Very delicate. Okay, so now let's take two paths and try to commute them. Where G has base point 1. This is crucial to the proof. So in principle, like a group is like uniform and it's homogeneous. The local behavior around every point is the same. Path components are homeomorphic. So it doesn't matter which base point you pick, you'll still get the same fundamental group. But for this argument, we're going to pick one because it's the most convenient thing. It's going to actually let us define a pointwise product of paths. So not the concatenation product, the pointwise product. So this is an operation on the loop space precisely because we've chosen to have base point one. So this product is going to be back in our loop space. Okay, so then we notice.
So like at each point t, you multiply like you would regularly.
Yeah,
Like
yeah.
two
Like
loop?
for,
Okay.
for each point t, you just have a point in one loop and a point in the other, and then they're just both elements of the group. So you
Oh, and then you just
multiply
multiply
them
the group. Yeah.
Yeah. Yeah, so
Okay,
this
yeah.
this and this, yeah. So this should be like the same operation as our group has.
Yes.
Yes. And then the concatenation operation is a different thing that we have to compare. So notice that doing this is, I should have written a homotopic to gamma zero concatenated with the left unit, and then times, pointwise times, right unit, and then the other unit, yeah. So we can relate these two operations together by, making space on one path and then, making space on the other path. So I'll draw a picture of this, the easiest way to see what's going on. So why we're basically already done just by noticing this completely innocuous thing. So here is our concatenation of paths. So we'll draw it. And then split it up into a product of two paths. It'll look like this. Okay, so really time there. So this is gamma zero and one. And I actually did mean to say equals here. That is not homotopic. As you can see from the picture, right? Doing one path and then the other is the same as doing one path and then sit still, times sit still, then do the other path. This is actually equals and not homotopic. But from here, now that we have these two, we can use our unit homotopes. To actually get the product of the two paths, the pointwise product of the two paths, and then continue along until you're doing the first path after resting, the second path before resting. So we multiply those two together. Now you have gamma 1 concatenated gamma 0. So there's your homotopy in pictures. And I encourage you to go write it down as well. You just have to use the formulas for these unit things. So what is it actually explicitly going on? First, so if you write this as gamma 0 times e minus, sorry, other way around. So then we have our product for our unit homotopies. You can just take the pointwise product of those two homotopies. You get the pointwise product of the maps. And then we do the pointwise homotopy. And then we multiply the reverses of the two homotopies to get the other side. And so this is going to give us So this was an exercise. My master's advisor said you should do an exercise, actually write down the formula that is this homotopy. I meant to do it, but I didn't. So yes, I think I never will.
There's no better time than 6 years later.
Yeah. Well, I didn't write anything on the back of that piece of paper. Okay. Okay, so that's the proof. Good enough, right? There's nothing wrong with this proof. It's a perfectly fine proof. It's a little ad hoc. I just noticed something clever and then did something tricky and then got an answer that just seems to be miraculous. It's not miraculous. The next proof I'm gonna, well, not the next proof, but one of the next proofs I'm going to talk about seems more miraculous and is going to be conceptually exactly the same as this proof. We're going to see that it's going to be the same. So first, what we can do is clean up this proof a little bit. Instead of messing around with all of these homotopies, we can just pass to the language of homotopy classes and just put equal signs in between everything. So next proof is going to be based on the fact that pi1 is a function. I haven't talked about that yet, i.e., so pi1 goes from pointed topological spaces to groups. So it'll take a pointed topological space and spit out a group. There also acts on morphism. So given F so we have morphism pi1f going between the fundamental groups. And there's sort of only one thing you could possibly do. You take a function alpha from the circle to x, and you turn it into a function from the circle to y by composing with f. What else gives you? And you have to show that this is well defined. This actually gives a homomorphism. And if you apply your pi1 to a composition of two functions, this is equal to applying the homomorphisms in the composition.
Sorry, what was alpha again? That was just a point, or
Yeah, alpha is just a function representing a homotopy class of maps. S1
in
to S.
okay in pi1.
Yeah.
So
So
and f composed of alpha
it's just also.
takes you into y. Okay, yeah, that makes sense. Yeah.
So I tend to use alpha when it's a function from the circle, and then I'll use gamma when it's like parametrized by the algebra.
Okay.
Yeah. Yeah. So yeah, I guess I also another notation for that is F star. Okay. Now we can do our proof number 2 by again just replacing a lot of those words and a lot of those explicit invocations of homotopies. I can just say equals, because everything's been sufficiently formalized. So what do we get? So we have our two maps, gamma 0, concatenated gamma 1, where this is the group operation. What are we doing here? Did I really do anything that helpful? Oh, not really. Okay. So this isn't actually that big of a change. We're just putting equal everywhere that we have on top.
Oh, it's the same at the end of it. Yeah.
Yeah, this is not quite a good idea. But we notice something kind of interesting, that the concatenation product is the same as our group product. We saw that also with the other board. It's a little more clear now that we've sort of abstracted away a lot of the homotopies that we've been doing. This is just getting fun. Okay.
Or gamma 0 or gamma 1 concatenated gamma 0.
Yeah. Like I said, we haven't actually done anything different yet. We just sort of cleaned up our language. Multiplicativity. Remember though, that the fundamental group is multiplicative. This is going to be the next thing. Apparently, I already did that page. So the fact that the fundamental group is multiplicative is going to play a big part at some point. I prepared all of these notes like very late at night, 5 days ago. Tend to forget going here. Okay. Yes, so multiplicativity. So given the topological group, so we take your I1G, I1G, by multiplicativity, we know that this is isomorphic to I1 of G plus G. That was important that we established that. Now we can use functoriality of the fundamental group on the star operation. Dot operation to get us back to G. So this also called dot, or dot. So this is the pointwise product. So it's not just defined on paths, it's defined on homotopy classes of paths as well, because we have this multiplication. I don't need. So we have a concatenation product now, and we have pointwise product. And we know they're actually the same. So I think I don't want to start a map board. I'm going to just state the theorem and prove it. So I'll just come back over here. Yeah, so it turns out that there's something extremely interesting happening in the background that's exploiting the interplay between these two operations. It's not a coincidence that they end up being. So this is called the Eckmann-Hilton theorem. I saw this for the first time. That's when my advisor said, no, you should really write down the formula because this theorem lets you prove this whole thing without writing down anything. So let S be a set. And let me say O plus and O times. I'm going to try really hard to distinguish these. Suppose these are two operations on S. Operations. The only thing I'm going to assume, the first thing I'm going to assume is that they have both two-sided inverses. So a priori, like use one in order to denote units. Sorry. Let's set myself up. So they both have two-sided units, and suppose they satisfy what's called the interchange law. So meaning that you take A composed with B, and you take C composed with D, and then you compose that using the other operation. You have this sort of weird flipping around of B and C, and you change the operations at the brackets. B. So what is this saying? This is actually, so this is a tensor morphism. And vice versa. So the interchange law, in words, the interchange law is saying that each of these operations is a morphism for the other one. And so this is not that extremely rare of a thing to happen. This can happen and it does happen. So if you have these two things, so operations satisfying the interchange law, and they have two-sided inverses, then the conclusion is that they are the same operation. They are associative and commutative. So we started with two-sided units and interchange law. And the conclusion is they are the same and they are associative and they're commutative. This should break your entire life. Like, there's no reason that should be true.
Please tell me you can prove it.
I have a proof.
Okay, good. Because I do not.
Yeah, you would definitely come up with it on your own given enough time.
Oh, wow, it's actually not that long.
It's purely formal and it's really fun. Okay, so first, notice that if you take 1 plus, by definition, it's a two-sided unit, so this is 1 plus plus 1 plus. And then we can use the unital properties of the other one.
It's one of these types of proofs.
These types of proofs. Okay, I'm definitely going to screw myself up with these numbers. Okay. 1, and then I want to use, oh no. Yeah, I changed notation because I didn't like doing the dots. We just have to use the right notation. Okay, I can do that. This is fine. Let's do O times this. So this is going to be O times O plus O plus. This is still O times, and then we have our plus in the middle. That makes sense.
Yeah.
Seems right. Then you just do interchange law. And you get the O times 1 plus 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 times. And so this is a unit, this is a unit, you get plus, 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 you get 1 plus. So therefore, same unit. So we can drop the subscript, thankfully, on the unit, not drive ourselves insane. And then we get that the two operations are the same very easily. So A, O times B, just by using the unit and the other operation. It's just a lot of like putting a unit in the middle.
Yeah.
Then applying the interchange law. So this is going to be A, O times 1 plus B, O times 1, O times B. And then you're just going to get A plus B. So they are the same. Once you've established they have the same unit, it's immediately to see that they are the same operation. And then commutativity and associativity also now follow right away. So let's do A, times B. Yeah, this time instead of putting ones in the middle, you put A and the B in the middle.
Variations of the same thing.
Such as so funny. Okay, so this is 1 O times B plus A times 1, and this is B O plus A, but we just saw that that's the same as B O plus.
Wait, how did you swap from the first line to the second line? How did you go 1 plus B to 1 times B?
That's an interchange law. Swap A and the B, and then the operations all
Oh
change.
shoot, did I misread it? Oh, I did. Okay, yeah. Good. Yeah.
There's nothing you can do.
Yeah.
You just do the interchange law and roll the times. And now finally, A plus B plus C. Yeah, I do this without, I just use the same operation. So this is A plus 1 plus B plus C. And then we do the interchange law, but we don't have to mess around with the operations, you know, they're the same. We'll just say that this is A plus B plus 1 plus C. We successfully moved our bracket over. So people who love universal algebra, like this is the stuff that do all day, every day. Yeah. Here comes proof number 3. Oh, I should have elaborated on the fact that what I'm erasing right now is still the proof. That the proof has now been abstracted into this very strange, very strange result called the Eckmann-Hilton theorem. So proof 3. So G topological group. So therefore, star and times are two-sided units of ops on I1. So we have these two, they have two-sided units because they actually have the same unit, we do that already. It's just a constant thing at the base point. And now we want to check the interchange law. So A concatenate B, and then pointwise times delta concatenate gamma. So if you write it down, what it will look like, here's your A concatenate B. You're going to pointwise multiply with delta gamma, okay, that was gamma. And this is obviously equal to multiplying those two first, and multiplying those two, and then concatenating the results together. So this is equal to the pointwise product, these two paths, concatenated with these two paths. So that's the interchange. So I'll do one of these. This is alpha, this one's delta, this one's beta, and this one's gamma. So this is alpha pointwise delta. And then concatenated with beta pointwise gamma. One thing I should point out, G itself doesn't have to be abelian. So you do have to be careful about the order that you do the pointwise product. But once the pointwise product is like out of the brackets and you're in a fundamental group, then you can move them around however you want. After you've established. So, right, so establishing the interchange law, we don't know yet whether it's commutative or not, so you do have to be really careful about where you put your things. Now that we've established the interchange law, we're done by Eckmann-Hilton. I1G is abelian. Cool. This is by Eckmann-Hilton. So this is like a really cool proof, and it's also the least satisfying proof because it's like complete like rabbit out of the hat. You just have this esoteric arcane knowledge that somehow gives you the magical result. You just have to verify interchange law, and that's it. So for the final part is going to be a new topic, I hope, for lots of people. Should hurry, but also at the same time, it's the last day. Okay. So we're going to abstractify more and start to think about broader contexts where you have a group that has like two group structures on it. So instead of, right, so we're going to take the Eckmann-Hilton theorem for the context for the Eckmann-Hilton theorem. And or at least for the case where instead of just being set, we have groups, we're going to try to elevate that up to like a categorical perspective. So that our objects are going to be like groups with an extra group structure stuff on top. And then try to see what happens out of that. You have a question? So we're going to call such. So the topic now is group objects. And these things can be defined in many categories, not all categories. The idea being that we can define a group object in a category by writing down our group axioms as a set of diagrams that are commutative. Once we have a set of diagrams that are commutative, you can define it for an arbitrary category where you can actually phrase and write down those diagrams. And so these diagrams involve products, and so it's natural to only consider we're doing this in the category with finite products. So let's see, be a category finite products. Including the empty product, I would like the empty product because that's a terminal object. Product zero things is terminal object. i.e., for all little c and c, there's a unique morphism from C to this term block. So I want to have zero products with zero things because I want to have terminal object in my category. So a group object in C is an object. What do I want to say? I used C in my notes. They will see me do it. And structure. So it's an object, but it has additional structure of being like a group. That structure is presented through morphism. So we have a multiplicative morphism, C cross C back to itself. So we're already using our products, sorry, we're already using the products in our category. We have an inversion morphism going from C back to itself. And we have a unit morphism from the terminal object to C. So just like, so this requires a little bit of explanation. So when we're talking about groups on sets, so what is our identity element? Well, that's a chosen element of our group. We want to talk about elements of sets without like going into the set. You can think about them as morphisms from the one set, like the singleton set to any other set, right? There's a canonical bijection for every set S between S itself and the set of functions from a singleton to S. It's a really, really weird way of, right? How is it bijection? Because a function just picks an element in it. For every element in F, there's some function.
You just like kind of associate it with like
Yeah.
F of whatever is associated to some element in the thing.
Yeah, so
Yeah,
this is your
okay.
function F, then you just set it into F of
F of X or F of star, yeah.
whatever the singleton.
Yeah,
So
okay.
it's a really dumb thing to do, but this is the way to generalize the idea of elements to an arbitrary category. Take your terminal object, which is a singleton category of sets, you start thinking about functions coming out of that terminal object. So every element, every object in your category has a unique morphism to the terminal object. So morphisms coming out of the terminal object are like interesting.
Yes.
So a group object, right? It's an element, object of our category that has these morphisms that are meant to satisfy some diagrams. They have to be. And these are going to look really familiar. We already wrote these down for loop spaces, except for loop spaces. They only commuted up to Ohmston. But here we're saying, okay, we're in an arbitrary category. We don't really know Ohmston meanings here. Let's just have them all commute on the nodes. So it's associative, unital. So we have a function C goes to C plus the terminal element. So this is always an isomorphous point, right? You have a terminal object in your category, the product with that terminal element, right? It's just like a singleton. All you're really doing is relabeling your object. So there's a phenomenon point isomorphism between these two things. From here, we can take a product of two things, one cross E into C cross C. So that this composition, what it does, where one is equal to the identity. So this composition takes an element. So if you think about this as like these were sets, this composition would take an element of C to itself cross the unit, the neutral element. And so of course, when you take the composition operation to C, this is supposed to be the identity. So similarly, similarly to the others. So this is equal, and then the inverse. It's like this. Start with C. Take the product of the identity and the inversion map, C cross C. Close the C, This is supposed to be, this is supposed to factor through the terminal morphism. This is a little bit more subtle than it was when we were doing it through the loop space. So here's the unit coming out of terminal object, and here's the canonical map from C to the terminal object. So this is being like a null homotopic map. It's like a constant map. This composition is supposed to be this constant.
Is there no notation for that map between the into the terminal object?
Probably.
Okay.
Oh, you could call it zero, even though it's not a zero object.
Yeah.
Yeah. It's kind of just like you think of the terminal object as sort of the trivial group. Okay. Good. People last big. Very good. Okay. So, for example, right, we just saw topological groups. So here's a bunch of these examples. So if C equals top star, we have topological groups. So notice, like, if we just started with top, our E would pick a base point for us. So a topological group is automatically pointed if it wasn't pointed to begin with. If it is pointed to begin with, then this E is supposed to be a pointed map. And so the unit thing would just choose the same base point again. So if you have a pointed space that is a topological group, or it is a group object, then your base point is the identity. There's nothing you can do about it. Start with an unpointed topological space and you impose a group object structure, right? That the neutral element of your space is canonically a base point now. The topological group. And like Tom pointed out, this is the smooth category. We have lead groups. This group object thing generalizes both topological groups and lead groups immediately. What about G equals group? What are the group objects? What do you think are the group objects in the category of groups? We will approach this problem. The audience have a guess.
If
What are the group objects in the category of groups? Then there any kind of
well, like obviously the first two are trivial.
Yeah.
But
there even like a hint throughout this entire talk that might actually help you guess what the group objects in the category of groups would be?
need something from like the terminal object back into.
Well, like I was saying, so we already have a structure of the category of groups. These are all going to be morphisms in the category of groups now.
Yeah.
So this is redundant information. This part is like extra because this is just a trivial group and then all you can do is map to the identity. So this part is actually redundant. Right?
Oh, so then I guess those two are just the operations in the group, no?
They are operations, but the G being an object in the group, like it is a self-contained group on its own. But then a group object is an additional group structure on top of that one, right? So the group objects in the category of groups, these are, like I was saying before, these are groups with an additional group structure.
Yeah, yeah.
So if these are morphisms, so if mu is a morphism, what does that mean? Well, this is actually a little subtle because this is the product group, right? We already have a group structure on this product. It's a point-wise, like coordinate-wise.
Okay, yeah.
Do the first two coordinates, comma, the second two coordinates. And so mu, what we're saying is that that's a group homomorphism. taking this group structure to that. What does this actually mean symbolically? The mu of, say, G1 comma G2, so one element of the product, times the product with H1 comma H2. But already in this there. So being a morphism precisely means that this is equal to mu G1 comma G2, and then pointwise product mu H1 comma H2. Okay, and so if we write this a little more suggestively, instead of putting mu out front, use it as an operation in between. So we could write this as G1 times over mu. This is just the operation I mean by applying mu to something. We write this like this. This side, what does that mean? This means we have, let's actually evaluate the product. So this is mu of G1 dot H1 on G2 dot H2. And then write it out with a slightly nicer notation. You have an updated guess. This is reminding you.
Oh my gosh.
So, like I said,
It's everywhere.
like I said, the fact that you use a morphism over this product, this translates to the fact that we just get the interchange problem between the inherent group structure and the added group structure, i.e. dot and to mu interchangeable. Therefore, mu equals dot.
Yeah.
And G is abelian. So therefore, the group objects group are abelian group. Right. Like I said, the proof is by Eckmann-Hilton. So the Eckmann-Hilton, which is surprisingly still on the boards. It felt like a rabbit from the hat to show that pi 1 of G is abelian when G is a topological group. We've elevated that formal nonsense to like the correct content for formal nonsense. And we found that it actually tells us what the group objects are in the category of the group. Like this result is like, this is more general. You can talk about monoids and semigroups or whatever. But this type of result is like specifically designed for concluding that these are abelian groups.
Doesn't always allow you to conclude some abelianness of whatever object you're talking about, because you said you could swap it to monoids or whatever, but
Yeah, you just have to start with two operations that have a two-sided unit, and they don't even have to be the same a priori. And then check the interchange law, and then you get associative and
and
commutative.
commutative. Okay.
So I'll just leave that there. It's nice. And then I'll finish off with the last proof, which is going to involve something about group objects that I haven't mentioned yet, which is really, really interesting. So proposition. So if C and P are categories with products, and F is a multiplicative functor which means that there's like a natural transformation between how do you say this correctly? Right, so for any object C and D and C, you want it to look like this. Maybe I can use C and C prime. So whatever is the correct way of saying that the functor distributes over the products, like there's some natural isomorphism that is happening at some highest level. Multiplicative functor means it distributes over the products. So if you go and look one more time at our definition of group objects, right, they're all defined in terms of products. something that preserves products also preserves terminal objects. You take a big F and just slap it on all of these diagrams and distribute over the products. What you get is something in G that satisfies all of these diagrams, where C is replaced by F. By G, I meant. So in other words, multiplicative functor sends group objects to group objects. So then F is, I'll write it group C, group objects in C. This is contained in the group objects of D. Okay, so last proof. And it's using nothing that we haven't already seen already. It's purely a corollary at this point. Okay, so or last proof, I'm going to say that. So we saw that I1 going from top star group is multiplicative. So therefore, I1 of our group objects in top star, well, these are all going to be group objects in group. And on this side, we saw that these are abelian groups, sorry, topological groups. And on this side, these are precisely the abelian groups. So that's the easiest proof. Is the one that has the most formal nonsense. Is that, okay, our fundamental group functor is multiplicative. We know what the group objects are on both sides, the domain and the codomain. We know the group objects here by Eckmann-Hilton. And those are just topological. So therefore, the fundamental group of a topological group is a B. So that's the last group of that fact. Say something else. Yeah, so this is kind of, I don't know. I found this inspiring because I learned it while I was also learning how to write computer programs. So what I really liked about this the most, that the original proof just has you sort of hyper-focused on one specific problem. You have a topological group and you're working with those wires to figure out why it's I1 is abelian. And then you come across this Eckmann-Hilton thing, which is this crazy sort of esoteric tech that like just works by magic. And then if you try to solve your little specific problem with this thing, it just seems like super, super overkill. But then this is kind of like the correct separation of interests, separation of concerns. It's like this really weird esoteric thing really is completely at home in this esoteric context, and not in thinking specifically about this. So the language of group objects and multiplicative functors allow you to sort of take your particular thing and move it into somewhere else where all of these esoteric stuff and do the job for you.
So is there like a language which allows us to translate? Oh, I guess this is what we've been talking about. I was going to ask the language which translates topological groups into like abelian groups, but that's exactly what we've been doing this entire time.
Yeah, and you can go backwards as well.
Yeah.
So there is this classifying space functor that I talked about in the summer. I talked about Milner's infinite join construction, which it's the easiest one to write down, but it's not the best. So there is a model for beam of G due to Milner again, so that
Okay, sorry, what was BG?
classifying space for G. So like the universal space for principal G bundles over their compact bases. So there is a model, there is a construction due to Milner, so that B of the product of two groups is naturally homeomorphic to BG cross BG. Easy from the theory that these are supposed to be homotopy equivalent. But to actually make it homeomorphic for all pairs G and H, that required a lot of work that Gollinger did because he's so smart. So in other words, there's a multiplicative model for B. So meaning that if G is an abelian group, so meaning it's a group object in the category of groups, so B goes from groups to pointed topological spaces. And so if G is an abelian group, then BG is a topological group. So it's not just some random classifying space, it's actually also a group. And is it going to be abelian? I think so. I think with a little bit more work, you can show that this is also abelian. And so you can just keep taking Bn.
En meaning like the classifying space for G.
Just take it in time. So you take BG, that's also a topological group. You can show that it's abelian. Maybe I'm lying, but I believe like if you start with an abelian group, BG is also going to be an abelian group.
Okay,
And so you can just take B again.
of that.
abelian.
Oh, okay.
So
And you'll just
B
continuously get abelian topological. Okay.
Yeah. So like BZ is S1, B S1, CP infinity, up to homotopy, right? So
Okay.
this is not this model. So
Yeah.
you can't just write down like, oh, this is the abelian group structure on CP infinity. It's kind of like an up to homotopy thing. But you can just keep continuing on forever. So this is what's called an Eilenberg-MacLane space KZ2. And so like B to the N of Z is a K Z N.
Okay.
So there is a model of KZN where it's absolutely is topological.
CP infinity is kind of cursed though.
That's not so bad.
Is it?
Uh,
I've only ever worked with finite dimensional stuff, so I assumed it would be fine.
It's
No,
contractible
no. Why would it be contracted?
or weak contractibility.
No. Oh, yeah. Here's a non-zero homotopy.
Isn't it?
You're thinking of the sphere, S infinity.
Yeah. But wasn't it homeomorphic to something CP infinity with some modification?
Remember last night in chat when you said that you would solve those rational homotopy theory problems easily? I'm not sure if I agree. You construct CP infinity out of S. So there's a circle action on CP infinity. It's just the complex scalars. It's sitting inside an infinite dimensional complex space, and the quotient by it is group action CP infinity. And so since this is contractible, this is a KZ1. This ends up being a BS1. Yeah, it's definitely not contractible.
What's the map between the two spaces?
It's the quotient. This is by definition. CP infinity is the quotient of S infinity by S.
Oh yeah, you're right. It's not contractible.
So you leave the long exact sequence of the homotopy groups to see that it's just homotopy of S1 but shifted. So it's only non-zero in one spot, but it is non-zero.
And
Yeah, it's
then
not that bad.
that's just pi one is not trivial for CP infinity.
By two. Right.
Oh yeah. I remember that. Yeah, you're right.
Tell
Yeah.
me what is the non-zero
Okay.
homotopy group and what the value is.
Okay, so the problem is just pi two of it. Okay.
It's not a problem.
Right.
It's just how it is.
The problem for not being contractible.
Yeah, sure. Yeah, well, Yeah. It's not. It's not a problem. Then you can add in a cell that would kill that homotopy group, but then you introduce higher.
Right, right. But if they're okay, then the whole thing would be okay.
I mean, you can just do that to any space.
Yeah.
You just start at the first non-trivial homotopy group and then add cells until it's dead. And then go to the higher homotopy groups and add more cells to kill the stuff in the
Keep on doing it.
but you're just gonna make a different space.
Can I go back, just because I'm like replaying the beginning of the lecture in my head? The part where we said E concatenated with gamma 0 ended up being gamma 1. That was in the proof just showing that it's abelian. And then we showed like, I
should
could
have
write it
written
out,
it
just
should have written it a different way. I don't think that's what I meant to say.
or you wrote like, was, sorry, because maybe I'm just thinking about it differently, but it was like, you started with this. Correct me if I'm wrong at this point. And then this was gamma 0. This guy.
Concatenated.
Oh, maybe that's one. Yes, it's true. And then we said that it was E concatenated with gamma 0. So this, no,
Maybe you're overlooking, or you're going like a weird direction.
no, like, okay, so what did we start with? We started with 0 concatenated with
Yeah.
1. Yeah.
And so did that.
Okay, yeah. We said that this was equal to,
It was what you just had. Yeah. As much as you can. Okay. We have to go for
yeah.
Yeah.
And then what did we say?
Then we applied the homotopy to get rid of the units, so now it's just gamma 0 dot.
Yeah, dot gamma 1. Yeah, and then,
You just do it backwards. You put the E on the left of gamma 0, and then on the right of gamma 1.
yeah, this. But then you said that this was gamma 1.
Add it. Yeah. I'm not saying that the left thing is gamma 1 and the right thing is gamma 0. I'm saying that that pointwise product is a concatenation. So we should draw it like right? So
And is this because the interchange or?
no, this is just because it's like you're multiplying two things together though, like this. You get gamma 0, and then you have like gamma 1. Right, so if you're going like this, then we're gonna get gamma 1 first and then gamma.
Real and true, yeah. Makes sense with the picture.
Yeah.
Yeah, okay. Yeah, I don't know why I wanted to do that, but yeah. Okay, good. That was nice. You know, it was really funny how it ended up on pointing down to the interchange law.
It's all easy.
So, yeah. The lecture could have been, or this seminar could have been like 5 minutes if we wanted it.
I don't remember if I had any other examples I wanted to get to you, so I should probably just stop. Thank you.
It was good. I like this one.
Yeah, no, this one is fun. It's not very hard to like prepare.